Hello, I'm Asbel Fontanez, and this is my partner.
Abdullah Karamish.
So we created a ALU, a decoder in ALU, which takes inputs from a keyboard and outputs it onto a 7 Seg display and a VGA monitor. So we'll just be quickly going over how it works and the different modules that we use to make everything work. So basically we start off with our main module, which is a decoder. It's called a Dec ALU or Decoder ALU. And basically we have inputs for clock, CPU reset, keyboard inputs, what you want this display to be doing, and then outputs for the 7 Seg display, the monitor, and the monitor. So basically we have 5 modules that are doing everything, and then we have an always block that decides between displaying the in digits from the keyboard, what's currently being inputted, or the out digits from the decoder, which Abdul will explain a little bit more about when he goes through the actual decoder. So first thing we're going to go over is what happens with the encoder. So basically we get inputs of clock, keyboard inputs, and we output our AB opcode digit holder and in, or if we're currently inputting that value or not. And then the first thing we do is we get information from the keyboard. Really, this has a module inside of it, which is retrieving 31 bits at a time. Bits at a time from the keyboard to represent all 4 different sync scan codes that you can get from the keyboard, depending on the different inputs that you, or the different letters that you type on the keyboard. And then from there, we're using, if we get a scan code of a key being released, we check what key it is released. And if it's a key that we want, then we store it into BCD. We take the BCD representation of it, so like 1 equals 1, 2 equals 2, type of thing. And then we have a new value, which is telling us if we've received a new value. And then we have valid, which tells us if that new value is valid. And then that's sent into a sentence creator. Honestly, should have been named word creator, since we're putting 2 nibbles together to create a byte. So it should have been word creator, but that's besides the point. But yeah, basically what we're doing there is dependent on if we have a new value and that new value is valid, we create a word of those different nibbles put together. And then from there, we want to truncate that sentence because BCD works great for displaying, but our ALU works on binary addition. So we have to truncate that sentence into binary. So that's what our BCD to bin is doing. And then we have what's called digit holder, which is basically just showing what's the output that should be displaying on the 7 Seg display. And yeah, so basically as our refresh rate changes, depending on what the 17th through 19th bytes are, we represent one of those different values. And I'll explain more about that when we go over the display 7 Seg. But then we go over on the negative edge of a new value, we check to see if it was either A, B, C represents O for output or for opcode. And then we either go to a different current state. So our current state is set to a 0, 1, or 2. And representative state is just so that it can actually be displayed on the digit on the display segment, or on the 7 Seg display, so that we actually know what state we're in and what value we're inputting. And then you basically reset at the beginning of each time, just so that you can actually create sentences. And then if you press enter, then you set reset equal to 1, and that basically just clears whatever was in the current sentence, and just clears it out so that you can go ahead and make a new sentence. But it does first assign A, B, or opcode to the truncated sentence. So yeah, that's that. And that's how we do the encoder. So the next step is the decoder, which Abdul will go over.
So the decoder is very similar to the lab 2. We'll have the output from the encoder, which is we get from the keyboard. We get the A, the operation code, the opcode, and B. The opcode is a 4-bit opcode, and then the decoder, it will convert it into a 3-bit operation and 1-bit mode. If the mode is 1, it do arithmetic operations, and if mode is 0, to do logical ones. And then the op and the mode and the cin would be the output of the decoder, which goes into the ALU. And in the ALU, it actually does like the operations, and it outputs the results and the cout. In this ALU, we used a carry look ahead adder instead of what we used in lab 2, the carry select.
Yep. And just to finish off decoder real quick, so after the decoder sends out the mode, op, and cin to the ALU does whatever operation it needs to. Then the ALU will output the output of what the operation was and the cout. And then dependent on what the user wants to currently display on the 7-seg display, if they want to show what opcode they put in, the A value and the B value they put in, then that will be on the digit holder. Otherwise, the out of the what's it called? The out of the ALU, or the output of the ALU, is shown. The output is binary from the ALU, so we have to send it through a bin to BCD converter, just so that we can correctly display it on the 7-seg display, which then will take me to the next module, which is actually our 7-seg display. And basically all we are doing here is we have a module for seg mapping and for anode select. So basically the anode select just moves through the anodes, or through each single 7-seg display, and it basically just allows you to change that specific anode that you're currently looking at, and that's just done through the refresh rate, which on every positive edge of 100 megahertz, you add 1 to it. And if I'm not mistaken, we're running it at 60 kilohertz. No, we're running it at, yeah, I think it's 60 kilohertz. I would have to look at it. I forget. But anyways, and then seg mapping will input a digit holder and will take out the output of seg. So it will map whatever the digit was that either the decoder wants to output or the encoder wants to output to an actual seg value. And then that's dependent on what anode you're on. But the seg mapping doesn't care about that, because the digit holders have always been assigned using the refresh rate. So it just maps it correctly. And that's what our this 7-seg does. And then we have finally our Vga controller. And this basically takes the cout that's given by the ALU, and it will display green if cout is 0. If it's 1, it displays red. In most cases, this is a representation of the output is valid or not. When it comes to some subtraction, that's not the case, just because you'll get a 1 in when doing some forms of subtraction, even though your output is correct. So in future iterations, that's something that we would adjust and fix, so that it's always green if your output is correct, and red if your output has some type of error due to overflow. But anyways, to finish off with the VGA controller, basically we have a VGA 640 by 480 module that goes in and basically just goes and refreshes through each pixel in your display of 600 by 480. And then from there, we just basically output X, Y, and data enable. And data enable basically just lets us know if we can actually be writing to that pixel. Because if you continuously just write a solid value for a color, it's not going to work. You have to be switching between a color and black, color and black, color and black, so that you're actually getting a color on the display. And then here we also have a counter, and basically on every positive edge, we add, and then whenever counter overflows, it turns on pixel strobe, and pixel strobe basically just allows the VGA 640 by 480 to do its job. So that's basically how the VGA controller works, and that's how all the modules work. So everything is then brought together again at the decoder ALU. And dependent on if we're inputting a value or not, it affects what is actually displaying on the 7Seg display. So once the user types in a valid input, which is either A, B, or O, to start inputting, the 7Seg display will switch to display the input and also show the character of what they're currently displaying on the leftmost screen. So either A, B, or O for each of those states. And on the rightmost two screens, they'll show the digits that are currently being typed by the user.
Hello, so this is our lab number 3 actual and hardware demo. So we're just going to go ahead and program the device and the actual files that we went over earlier. And then what you will see is that is our current output. That's now showing your opcode, your A, your B. So if we just go ahead and let's say we were to type O, now you can see here it shows us O for output. This shows that the one shows that we're currently in input mode, and then this is where we would go ahead and type in our numbers. So if we were to go ahead and type in 12, you can see that it changes to 12. And then if we wanted to actually change the number to actually be 2, we could do that. Or if we wanted to change it to be, let's say 10, we could go all the way back and now input 10. If I press, we're actually going to put it into 5, we're going to put it into mode 4, which is addition. So if we type in, you'll see that now the opcode is 4. So then let's go ahead and set A to be 5. So if we type in 5, you can see there. Let's turn B to be 4. And as you can see, now it shows B. So if we were to do that, we have that. And then if we were to bring this back, now you can see that 5 plus 4 is 9. And then our C out, which happens from addition, is green. So we know that we're not having overflow issues or anything like that. So instead, let's say we were to do, we wanted to change our operation code. Oh, by the way, if we're still in that mode and we still type O, we'll still go into input mode. So let's say we want to do subtraction, which if I'm not mistaken is 5, and we press enter, you'll see that it automatically switches, and 5 minus 4 is 1. You'll get red, even though it is a valid output. You get red from the C out, which is something that we would change in further iterations where we just keep green always whenever it's a valid input and we don't directly tie it into our Cout. So yeah, that's what you basically see. And so the reason we did it this way is so that the user can easily understand how they're inputting values by seeing what's the current input that they're putting in, with the O, A, or B being here. And then they can easily type in numbers. If they mistype or something like that, they can just backspace like a normal text editor instead of having to do a complete refresh restart of it. And then by allowing them to see what their current operation code is and everything, that allows them to basically just make sure that that what they typed in was the correct thing that they wanted. And if they want to see the actual output of the operation that they just requested, they just switch the switch and they'll get the operation, and they can see their Cout value with either red or green, being for 0 and red being for 1. And further iterations, we'll make sure that the red would be bad overflow and green would be a good input. But yeah, that's basically it. So thank you for watching or looking over this demo. So yeah, have a nice day.